Yeah, he's in our the same department.
Yeah, I have a MEMS background, so I used to interact with him once in a while.
Okay. Oh yeah, no wonder he's doing MEMS. Yeah.
Yeah. The scenery is very nice. I think maybe you can put that one with the snow.
Mm-hmm.
But it's, yeah, very. So this is the campus or the city, or is city nearby?
Campus. It's a campus.
Where's the city? Is there a city near Boulder?
The city is near Boulder. Yes. Yeah. See this studio and campus here. City is somewhere on the right side. Some right here.
How big is the city?
It's not too big. It's I believe it's somewhere like 200,000 people. Boulder.
Okay.
Yeah. Can you see my mouse?
Yes, I see your mouse. Yes, I see
Okay,
it.
good. Yeah, that's useful for the topic.
That's your mouse.
Yeah, the school is located in the foot of the mountain, and the Rocky Mountain is right behind.
I see. So maybe we get started. It's 3 minutes after. Good morning, everyone. Welcome to another Terasaki Talk series. Today we have Professor Shayun Ding from UC Boulder. He is currently an assistant professor of mechanical engineering and biomedical engineering, and Bruce Anderson Engineering Faculty Fellow at University of Colorado Boulder. Before CU Boulder, he joined Colorado in 2017. Before, he was a postdoctoral associate at MIT. His current interests are on microfluidics or MicroNano Manipulation, cell mechanics, intercellular drug delivery. He has published so far 30 plus journal papers, 8 US patents, and 20 plus international conference presentations. He has won many awards: NIH MIRA Award, Biomaterial Science Emerging Investigators 2021 Award, Colorado Lab Venture Challenge Award, Keck Foundation Medical Research Grants, CCTSI Novel Method Development Pilot Award, Baxter Young Investigator Award, Best Student Paper Competition Award in IEEE IUS, Rasta Mandela Roy Innovation and Materials Research Award. Floor is yours.
All right, thank you, Mehmet. Thank you for your invitation to give a seminar to introduce some of my research progress in the area of micro-nano particle manipulation. Okay. So everybody know manipulation is to control the movement of objects. And human has the capability to manipulate giant objects with the help of robotic arm, right? And for smaller objects like football, you can easily use your hand to control it. For a smaller objects like small diamond or small component in the watch, then you need the help of a metal tweezer. How about for even smaller particles like biological cells or even molecules? How can we achieve the manipulation of those tiny things? The gold standard for such micro-nano manipulation is optical tweezer, where you shine a laser or high-intensity light towards the objects, and the light has an intensity gradient from the center to the edge, so that the particles or cells could be trapped in the middle of the laser beam. And optical tweezer has been so powerful and versatile. However, the setup of optical tweezers, although it's got a standard, the setup is very expensive and bulky, and the throughput is not great, right? You can manipulate one cell or maybe a few number of cells or particles. Also, it might generate some side effects to particularly for some higher particles like cells or molecules, such as photobleaching and thermal and others. Optical tweezer has been demonstrated its powerful capability for particles from nanometer scale to tens of micrometer scale. For objects larger than millimeter scale, you can easily handle it with pipette tip or with tweezer. But for particles range from tens of micrometers, that's such as 100 micrometer, right, up to millimeter scale, such as currently very popular organoids or some small model organism. Is there any way to do it? To be more general, a desirable technology for MicroNano manipulation, especially for biomedical applications, people expect non-invasiveness and versatility, miniaturized and low cost, and hopefully can be compatible with other on-chip systems. And here we propose the surface acoustic wave enabled acoustic manipulation. Here's the outline. First, in this seminar, I will briefly talk about the mechanism of such acoustic manipulation, and then we will report some of the most recent research progress of such acoustic manipulation, covering from nanometer scale up to millimeter scale. So first is the mechanism. Surface acoustic wave is a wave that propagates on the surface. And here you can see this is a typical propagation of a Rayleigh wave. Rayleigh wave is a typical mode of surface wave. To have an idea of such surface wave propagation, you can throw a stone. Imagine throwing a stone into a quiet lake. You will see the water wave, right? That pretty much catch the idea of such surface wave, especially Rayleigh wave. Not exact same, but similar enough. And because it's first comprehensively studied by Rayleigh, so we call this type of wave Rayleigh wave. And this source can be easily generated by using piezoelectro materials, simply by depositing a layer of electrode we call interdigital transducer, IDT, on top of the piezo substrate. And then you apply an AC signal, then you can generate this surface wave. From high school physics book, we learned that when two identical waves propagate towards each other, then you can form a standing wave. And in the standing wave, you will see the pressure node and the antinode with minimum and maximum pressure. By changing either the frequency or the phase of these two identical waves, then you can simply change the position of the pressure node. And we also learned that in such a standing wave field, particles, right, or cells can be trapped in the pressure node. And these particles trapped in this pressure node by a force called acoustic radiation force. And this acoustic radiation force can be expressed by the equation here. And the simulation shows the pressure distribution in such standing wave field. And the pressure gradient actually determine the acoustic radiation force. And our computation to show that this acoustic radiation force matches well with our experimental measurement of the data plot. Based on this concept, we designed this acoustic device where we have four IDTs, four interdigital transducer IDTs surrounding a microfluidic chamber in the middle. By changing the signal, we can change the position of the pressure node, then we can change the particles trapped in the pressure node. Fabrication-wise, it's quite a standard. We use a standard photolithography, lift-off, and silicon etching to make those electrodes as IDT and make the channel mode, and then use PDMS, which is popular to make this microfluidic chamber. And the final device is quite simple and tiny and small. Based on this device, we demonstrate the capability of moving particles. Right? We move the particles here in X direction and back and forth for 100 cycles, while which show the displacement in red, and the blue shows the displacement in Y direction where there's no movement. And we can continuously move particles in one direction. And this trajectory shows the displacement of particles in only one direction. Of course, we can control the particle movement in X, Y direction independently. So based on this acoustic manipulation platform, we have demonstrated quite a lot of applications, such as tunable cell particle patterning for cell culture and the cells droplet sorting, or some liquid alignment, liquid crystal alignment, and the single cell manipulation or label-free cancer separation based on different property of the cells. And as you see so far, majority of the application of this acoustic manipulation is in cellular scale. Now, I will particularly focus on some recent research progress of such acoustic manipulation, covering from nanometer scale to millimeter scale. First, in nanometer scale, we developed an acoustic thermal shift assay for protein characterization. Thermal shift assay is a very standard and widely used assay for protein characterization. The idea is quite simple and straightforward. We all know that protein can partially dissolve in aqueous solution, that is water. And when you increase the temperature of the solution, the protein will start to denature and then start to precipitate. So when you keep increasing the temperature, then all the protein will precipitate. Then you come up a curve, like blue here, shows the protein solubility as a function of temperature. We call this curve melting curve. And this curve indicates the protein solubility, of course, and its thermodynamic property. When a protein bonds to another molecule, ligand, right? We call ligand or other drug, or even other protein. Its melting curve will shift. That means when bonded to another molecule, the protein thermodynamic property will change. By measuring such melting curve shift, you can measure whether the protein will interact with another molecule or not. And this is a very popular way to measure such protein interactions. And there are many ways to measure such melting curve, right? There are some like optical method to measure its scattering or fluorescent change, or electrical method, or even some using mass spectrometry to directly measure the amount of proteins. So far, however, all these protein thermal shift assay techniques, they have at least 2 or more of the drawbacks here, such as low throughput, limited sensitivity, relatively high protein consumption, complex sample preparation, or expensive and bulk instrument. Let me give you an example. Mass spectrometry-based thermal shift assay is a powerful tool and has been used widely in protein analysis, particularly proteomics study. The working flow is like this. You first divide an aliquot sample of interest into tens or even hundreds of different vials, and then you heat each vial to certain temperature. This melting curve is a function of the solubility to temperature, right? So you need to heat each vial to a certain temperature, and then you centrifuge and collect the precipitates of the protein, and then use some mass spectrometry to measure the amount and the type of proteins. Those processes takes a long time, days or even longer. Although it provides very high sensitivity, but it requires relatively high protein consumption, and it requires complex sample preparation. And of course, this mass spectrometry equipment is very expensive and bulky. Another typical method is immunoblotting, or you call it Western blot, right? So you can aliquot the protein sample of interest into tens or hundreds of vials and heat to different temperature. And then you take the sample, unprecipitated sample, and run the gel in the gel, and then you measure the intensity. And this Western blot provide limited sensitivity and also require high protein consumption and a complex sample preparation. It takes at least a few hours. And although it's not that expensive, but it's still on top, table on top. And the throughput, again, is not great for the Western blots. Here, we developed a technology called acoustic thermal shift assay, which provides a rapid, low-cost, miniaturized, and a sensitive and label-free approach for such protein analysis. The device schematic is quite simple, as shown here. We have two IDTs that can generate SAW, surface acoustic wave, towards the middle of the chamber. And this is the real device, look like. It's small and on chip. When we look into this small chamber, the acoustic will generate heat somehow to denature the protein. And then second, simultaneously almost, the acoustic radiation force plus acoustic induced streaming direct force together, work together, will concentrate to achieve this protein precipitate assembly. This can significantly enhance the local concentration of the protein. By measuring this protein precipitate process, we can come up with a curve we call acoustic melting curve. When protein combine a bond with other molecular ligand, then we can see a curve shift. So by measuring this curve shift, we know whether this protein will interact with ligand or not. And this whole process takes only about 1 minute or less, depends on the conditions. And here's an example of such a process. First, the protein dissolves in the aqueous solution and it's almost transparent. Now when we turn on our device, and here we use a hemoglobin protein. At about 20 seconds, the protein starts to precipitate. And in another 20 seconds, 10 to 20 seconds, then the protein will be aggregate and form clusters. So by measuring these protein precipitation dynamics, we know the protein properties. Here, we use two standard protein model. One is a hemoglobin, HB. Another is a citrate synthesis, CS. And we see that before and after this acoustic, we see the protein assembly show up. All right. And here, using these two models, we measure hemoglobin and the pore, which is known for their interaction. And that means pore will bond to hemoglobin in the solution. Let's look at hemoglobin pore first. In figure A, using our HR technology, we see that the black curve shows the melting curve of hemoglobin only. And in blue and red, we show the melting curve of hemoglobin mixed with low and high concentration of pore. And we see that when the hemoglobin mix with pore, they will interact, and that will cause the hemoglobin thermodynamic property change, and thus the melting curve shift. We compare our HR technology with other two commercial available and popular methods. DSF, differential scanning fluorometry, or BCA assay. Those are the two popular methods to measure the protein thermal shift assay. And we say that DSF simply cannot measure the hemoglobin signal because of the hemoglobin has the entrant fluorescent, and the DSF is based on the protein fluorescent light or scattering. And the BCA shows some reasonable shift, but not as sensitive as HR. And then we test the second protein interaction model, CS and OAA. They're also known for their interaction between each other. And as you can see in our system, for CS only, we have a curve in black color. And the CS with the low concentration OA, we see the blue curve. And the red shows the high concentration of OA. And it's very clear. The melting time shift is quite obvious. For DSF, again, the temperature shift is very small. And for the BCA, again, is not as obvious as HR. To quantify the sensitivity of those three methods, here we define the sensitivity as the ratio of delta signal over the total background signal. Here we show that the pink shows the HR technology, the sensitivity of HR, and the blue is the sensitivity of BSA for the protein of hemoglobin plus pore, because DSF cannot measure hemoglobin. HR shows a much higher sensitivity. And for the CS and the OAA model, the HR also shows very high sensitivity than the other two. So basically, for hemoglobin, HR shows 7 times higher sensitivity than BSA. And for CS-OA, HR shows 9 times or 34 times higher than BCA or DSF method. Moreover, we did some more exploration of the technology. For example, we measure how this HR technology sensitivity to the concentration of both base protein or the ligand, and we try to see where is the limitation is. But again, this is based on current without optimized version. And we also measure at different power level, and we see the temperature of the device induced by the acoustic is different. Higher power, of course, will lead higher temperature. And the higher temperature, higher power lead to high temperature and lead to shorter time of the measurement, right? At the 2 words, for example, it takes about 2 minutes to generate this curve to complete the measurement. And for 3 words, it takes about 1 minute. And for the relative shift, which is the sensitivity wise, there's no obvious difference. No matter high and low power level, the sensitivity remains similar. And more interesting, we also try to test our technology for some diagnosis purpose, sickle cell disease. Sickle cell disease basically is a disease induced by hemoglobin mutation. In sickle cell disease patient, the hemoglobin cannot properly carry oxygen. And that's because of one mutation in the hemoglobin. And such small mutation will cause not only the hemoglobin function change, but also cause its thermodynamic property change. Here, using HR, we can easily differentiate sickle cell disease hemoglobin from control where is health and normal hemoglobin. While for other methods like ESF or BCA, they simply cannot tell this difference. So this triggers us to think this could be a effective way for some protein-based disease diagnosis. Keep in mind, this process only takes 1 minute, so it could be a good potential for diagnosis purpose. And we're still working, collaborating with medical campus scientists to explore its applications for diagnosis. Now, after showing this nanometer scale acoustic manipulation, then we will show some application in micrometer scale. In micrometer scale, you will see tens of or even hundreds of applications for cell-based study. Now, today here, I will particularly introduce the application in internal structure manipulation of endoskeletal droplet. That means you can control the internal structure of a droplet, which has never been shown before. So a little bit of background. A multi-emotion droplet is the droplet system that droplet inside a droplet. And the majority of such multi-emotion droplet system is liquid droplet. You have liquid droplet inside another liquid drop and another liquid droplet. And more recently, people show that they can make a solid liquid multi-emotion droplet system. We call it endoskeletal droplet. You have a solid inside a liquid droplet so that you can control the liquid droplet. And this endoskeletal droplet, the solid is a network structure of solids. So our group recently made such endoskeletal droplet with a single disk inside a liquid droplet. Why we do this? Because this endoskeletal droplet, you can easily control its melting and evaporation temperature by changing the ratio of the solid and the liquid, which shows great potential for acoustic imaging or photoacoustic imaging. But when we look at this endoskeletal droplet we generate, I feel really frustrated because it looks very messy. And my philosophy is simpler, better. So we design a microfluidic device that can generate a very uniform droplet system, a very uniform endoskeletal droplet with a precise control on both the size and the ratio of solid and the liquid. And the size is very uniform. And then, surprisingly, by placing this skeletal droplet in the acoustic field, we found that those droplets, they will form clusters, which is expected. But what surprised me is that the disk inside the droplet, they also somehow align and form a very uniform and special orientation. Then we explore deeper into this disk orientation. And we found that no matter in 2, 3, 4, 5, or 6, 7 droplet clusters, almost all the disks inside, they, after turn on the saw, they align vertically, except for the case where in the large cluster where the center droplet, the disk is still vertically, is still parallel to the surface. And for a single droplet case, the disk inside, after acoustic is on, the disk will become parallel to the surface. And for 2 droplets case, the disk will somehow realign, and with the angle not perfectly vertical or not perfectly horizontal, but somewhere with the angle. Then that trigger my curiosity. So what's the governing rule inside and how to control it? So we developed a model to study the behavior of the disk inside the droplet. And our model should perfectly match well with the experimental observation. And no matter in 1, 2, 3 or more droplet systems. Right, so let me explain one by one. So here, this is the experimental setup, how we control or manipulate those internal disk structure inside the droplet. And we found that this droplet first will form clusters instead of those chain, the line pattern. That is because of the scattering force from the neighboring particles. Okay, so I'm not going to deep here. I'm not going to jump too deep here. What I want to say is here, this is a cross-section of the microfluidic chamber. And let's look at this two droplet case. In this two droplet case, we have in the standing wave field, we have one force called primary force that will push the disk upwards in Z direction. And another force called the secondary force that is due to the scattering acoustic from the neighboring droplet. This secondary force will push the droplet towards the side. And the bottom equation shows the formula shows the force. And the net force will push the disk towards Z direction with some angle to the horizontal plane. And whether the disk align vertically or horizontally, it depends on these two forces, the primary force and the secondary force. And our quick simulation shows that at low frequency and high frequency, you will see the angle of the disk in two droplet system, they are different. At higher frequency, the disk tend to be vertical. That is because, as you can see from the equation, the primary force is less sensitive than the frequency. So that means the secondary force is more sensitive to frequency. When you increase frequency, then the secondary force will dominate and push the disk to the side to push it to stand. And for the 3 droplet cluster, it's the similar. And for 10 megahertz or 20 megahertz, for 10 megahertz, the disk is almost parallel to the surface, to the horizontal plane. At 20 megahertz, the disk is almost standing. So that explains well why this disk, explain the disk behavior on the different frequency or on the different droplet clusters. And this is a good image to show that by simply changing the frequency, then we can switch the orientation of the disk inside the droplet. And this way, potentially we can use this for some kind of light shutter. Right, when we change the frequency between low and high frequency, we can see the light transmission, light intensity on and off. This reminds me for some potential applications for organoids clusters, where we can potentially control the internal structure of organoid. Organoids are the cluster of many tens or even hundreds of cells. Thirdly, we will move to millimeter scale acoustic manipulation, in particularly small animal manipulation. C. elegans is a model organism for research in developmental biology or neurology studies. And it is widely used as a model organism because it is simple to study, it's easy to grow, it's transparent, and also C. elegans is one of the simplest organisms with a nervous system. So it's widely used. And this C. elegans, typically adult C. elegans, it has a length of about somewhere 1 millimeter scale. For adult worm, well, it's okay. You probably can use a pipette to control, to move the C. elegans, right? But for larva, which is a few hundred, like 200, 300 micrometer, it's tricky to use a pipette tip, but it's still possible if you're very experienced. But think about that. If you want to handle or want to process tens or hundreds of C. elegans, that'll be nightmare, right? My collaborator who study C. elegans, they told me for 1 or 2, a small number of C. elegans, that's fine. But if you want to process tens or hundreds, that's nightmare. It takes a lot of time. Moreover, the pipette-based, if you use a pipette to control the C. elegans, you have a hard contact. So the pipette tip might somehow hurt or damage the worm. Here, we show that we can use our device to precisely control the worm contactlessly. So this video shows the movement of C. elegans under acoustic wave. Now it's power off, then you can see worm swim. When we turn on device, we trap the worm and then we move, right? And we turn off again, and then the worm will become active again. And the trajectory shows how we move the worm. We move the worm from in Y direction and X direction and Y direction again. Moreover, we can use our acoustic approach to immobilize, stretch the worm, which is very important for imaging purpose. As you know, even you can use pipette to manipulate the worm, to move them, but you cannot totally freeze them, right? If you use chemical method to freeze the worm, then it will affect the worm's physiological function. And if you use other physical method like gel and glass, you can immobilize the whole worm, but not completely. It's still, the worm might still twitch a little bit. That's what I learned from the C. elegans group. So here we propose to use this acoustic wave to totally freeze the worm. And the device is quite straightforward. We apply the acoustic wave towards the chamber. The chamber will hold the worm for imaging. And before acoustic, you will see the worm will swim, and you cannot take a high resolution image. But when we turn on our device with acoustics, then the worm will be freezed. And we compare with the our acoustic induced worm immobilization with heat-based method. So the left one shows, this is a video. It's not on real time, it's 5 times faster for both. So you will see when we heat the plate will freeze the worm. And it takes about 1 minute to totally freeze the worm until the temperature reaches somewhere 34, 35 degrees C. Of course, this process is not reversible. That means that will almost kill the worm. And in our device, using acoustic wave, we can freeze the worm in about a few 15 to 20 seconds, and up to the temperature of somewhere about 28 degrees C. And this process is reversible. Here, we measure the worm swimming activity. We call bending frequency. That is how much bends the worm, how much time the worm bend per second. And here we track 3 worms. Before this green line, right, the device is off, the worms so basically freely swim. Once we turn on our device at high power level, 2 watts in this case, the worm bending frequency immediately drop to some level, but not totally, not completely freeze. And for about 60 seconds around, then the worm almost completely freeze, not moving. And then we switch our device to low power level to maintain such immobilized status. And we keep that for 1 minute or even longer. For that time window is enough for imaging, even confocal imaging. And after that, after imaging, we turn off our device, turn off the power. Then you can see the worm almost immediately after a few seconds, they will recover and become active again to reach the original level. And we have tested this immobilization on and off for continuously for 3 days. And we did some imaging to show the neuron synapse activities. And we're still in the process. And the second application of small animal manipulation is to modulate swimming exercise. Here is the device, and we have 2 IDTs that can control the acoustic wave towards the chamber in the middle. The chamber will contain worms for study. And the right shows the fluid. We put some particles there to trace the fluid streaming, and then we track the fluid velocity. All right. And the left one shows the fluid streaming by tracing the particles. And we see we can generate this fluid streaming inside the chamber. And the right video shows the worm swimming activity. You can see the worm are swimming, and I can replay again. You can see the small particles are moving, right? The fluids, that is streaming. And the worms swimming, in general, they are swimming against the flow. And why we study this? You know, Parkinson's disease is a very, is a disease affect a lot of people, and it's caused by the neuron dysfunction. People believe that maybe exercise can help prevent such Parkinson's disease, or may not. Here, that's why we use our device to control the exercise of worm to study how the Parkinson's disease will affect this neuron. How the Parkinson's disease neuron will be affected by the exercise. So here, our device, we show that we can control the particle velocity, of course, the fluid streaming, and different power level, we can control the particle velocity, and that's the fluid streaming velocity. And we also measure the temperature, because you don't want to heat the device too high so that it will kill or affect the worm physiological function. So we test different power level. We see that at high power level, the temperature will increase about 3 degrees C, and at middle power level, 0.25 watts in our device, the temperature increased by 1 degree C around, and it provides reasonable acoustic streaming. So we will pick this 0.25 watts in our case. And because our goal is to measure, to control or modulate the worm swimming activity, right? So we first measure how this device can control the worm swimming exercise. We measure again the bending frequency of the worm, where is how fast the worm swim. And before the acoustic, the bending frequency is somewhere about 1.5. That means the worm will bend 1.5 times per second. When we turn on our device, the worm significantly increase their bending frequency. That is rate increased to about 1.7. And even 30 seconds after turning off the device, turning off the power, the worm still maintain their swimming exercise. So that shows that clearly our device can help control the swimming exercise intensity. And of course, we can also control the duration by controlling the on time of the device. And then we use a Parkinson's disease model worm, where the Parkinson, where the worm will express alpha synuclein or alpha-syn. It's a protein associated with Parkinson's disease, which is well known. And this worm also co-expressed the GFP with dopaminergic neuron cells, and we found that after certain exercise, we found reduction of the neuron loss of DA, dopaminergic neuron cell. This shows that the exercise can help prevent this Parkinson's disease, partially at least, based on our current results. And we are doing more experiment to further confirm our conclusion. All right. Okay, so finally, it's to summarize, we have demonstrated the acoustic manipulation for micronano particles, covering nanoparticles, where we can use acoustic thermal shift assay to characterize protein interactions. And we can also use this acoustic manipulation to control the internal structure of endoskeletal droplet, which is also the first time of such kind of manipulation. And in millimeter scale, we demonstrate the application of elegans for imaging purpose by immobilizing the worm or modulate the swimming exercise of the worm for Parkinson's disease study. And this is the first demonstration of swimming exercise modulation of the worms. Finally, I would like to acknowledge all my students and the postdoc who did all the experiments, and also the help from collaborators, and also thank the funding support from all the foundations. And last but not least, thank you all of you to attend this seminar. And thank you. I'm ready for questions.
Thank you for the great talk, Professor Ding. Several questions came in. How can we vary the power of surface acoustic wave in the fabricated device? Do we need a new device for every time we want to change the power of SAW?
Okay, good question. We can, the device is driven and powered by equipment called a function generator. Of course, we can use an electric circuit board to replace the function generator for real product. Right now, we use a function generator. And the function generator, you can tune the output power applying to the device. So we simply tune the function generator to control the power.
Nice, thank you. Can this method, acoustic protein separation described that would precipitate and denature proteins in seconds, be applied to assess the mitochondrial proteins among the cytoplasmic fraction?
I'm sorry, pardon, can you repeat the question again?
Let me repeat again. Can this method, acoustic protein separation described that would precipitate and denature proteins in seconds, be applied to assess the mitochondrial proteins among the cytoplasmic fraction?
That's a good question. I don't know the answer. And that's something we will explore next because I can tell some unpublished results. We can use method to not only denature protein, but also can break the cell membrane. So that can release the protein from inside the cell. And the issue is how to differentiate different type of proteins. That's something we don't know. And that's something we'll figure out in our next step. Good question.
Thank you. Could you tell us which material did you use to make your IDTs?
Okay, so the IDT, the substrate is piezo electro materials, and technically any piezo material can be used for this device. Here, in our case, we use lithium niobate as a substrate, and for the electrode, technically any metal can be used as an electrode, but here we use chromium and gold because of its low conductivity. But many people use aluminum.
I see. What are the frequencies of SAW in nanometer and micron scale?
It's a broad range. We use somewhere like 10 megahertz to a few hundred megahertz. And for the particularly for this nanoprotein, we use somewhere, I believe somewhere a few 10 megahertz, like 80 megahertz or 50 megahertz. And for the micron, we use 20 to 30 megahertz.
Okay, thank you. How do you generate the disk inside the endoskeletal droplet? Can you also explain more how you see it being applied for organoid applications?
Okay, that's a good question. Yeah, because of the limited time and also the internal structure of disk manipulation is more towards physics, not bio, so I didn't explain too deep in that. The acoustic can propagate and penetrate into the droplet and reach the disk. So that's how it can manipulate the disk inside. And also because the disk has different acoustic property from the surrounding droplet liquid. And for the organelle, yeah, I'm chatting with a potential collaborator who working on organoids. Well, I'm not an expert in the organoid, but for some organoid, you have different structures, different type of cells, right? Where you have a shell structure of cells, and the inside you might have some kind of media, and together with some another type of cells inside or another biomaterials inside. In that case, we can potentially use the acoustic to control the bioparticle or cells inside the organelle. That's my assumption, but we haven't proved that yet. So that's something we will try to explore.
Thank you. Are there limitations that should be considered in terms of protein types that can be studied using acoustic separation method?
So for protein separation?
Yeah, when you want to separate the proteins, are there limitations? Or can you separate all proteins?
Well, I don't think we can separate the protein in this particular case. Here we denature the protein and then measure the protein interactions with other ligands. I don't know if I answered the question, but
maybe the person didn't get it. Can you tell us more details about the micromanipulation of endoskeletal droplet for organoid application?
Okay, is this the same question to the previous?
No, that's a different one. That's a different one.
Okay. Again, this is just in the conversation stage with a potential collaborator, and they are studying some organoids where they have some kind of one cell type on the outside, and the inside they have another type of cells with some potential media inside. So in that case, we can apply our acoustic to control the cell or biomaterials inside the organoids. So that's what we think at this moment.
Okay. What is the typical value of temperature increase in acoustic thermal shift assay system? Does this increase in temperature pose a problem for biological systems?
That's a good question. Actually, for the protein thermal shift assay, we need to increase the temperature of the protein sample so that the protein can denature and precipitate. The key is to control the temperature at different temperature point, and then we measure the protein precipitates at each temperature point. And the current method, you prepare tens or hundreds of protein sample and heat temperature to a certain level on each sample, and then you measure the solubility. And in our case, we continuously increase temperature and then measure the dynamics so that we can measure the protein thermodynamic, the protein precipitate dynamics, and then measure its thermodynamics. So that we purposely increase the temperature.
Thank you. Is there a problem with vibration resonance that can cause a cell to burst?
I'm sorry,
Is there a problem with the vibration resonance that can make the cell burst, explode?
Oh, that's a good question. So far, we haven't observed any issue with the vibration cause the cell burst at this moment. But if you add some structure there near the cell, and this structure, example, sharp edge, right? They will vibrate, and they might break the cell, and people have shown that. But in our case, we don't just place the cell in the liquid, no other structures, it will not.
I see. How did you monitor the variation in the hemoglobin protein versus the temperature?
Oh, power level. We will calibrate, right, without cell in just liquid. We measure temperature as a function of the power and the time so that we can know the temperature. And we have a thermal probe and into the channel, so we know the temperature as a function of time and the power. That's how we calibrate the temperature.
Can you describe the trade-off between the acoustic induced temperature and the acoustic radiation force to pattern the target proteins?
Oh, yeah. That's a good one. So you catch the point. So for the protein thermal shift assay, right, acoustic thermal shift assay, we use both the acoustic temperature and the acoustic force. And we first use acoustic heating to heat the temperature to cause the protein to denature and precipitate. As you know, when the protein precipitates, they're randomly distributed everywhere. And if we simply use heating and measure, then the sensitivity is not great. It's no big difference from other methods like DSF or BCA. Here, what stands our technology from others is that besides the heating, our acoustic can concentrate those precipitate protein locally. So they form aggregations. This will significantly enhance the local signal, the local concentration and the signal of the protein, so that we can have a higher sensitivity of the measurement. And regarding how the acoustic force can aggregate those proteins, there are two mechanisms. One is directly the acoustic radiation force. Another is the acoustic will cause some kind of streaming in the chamber. This streaming will apply some drag force that can help aggregate those proteins. So it's like two types of force there.
Thank you. It's a very powerful technology you're showing. I've seen that you're assembling things. Can you also detach or unassemble using your technology?
Detach cells?
Cells or particles, you can assemble particles 3, 5, 10, 20, but can you selectively start removing them as well?
Right now, when we turn on the device, right, we can assemble them. And when we turn off, then the particles will naturally disperse.
Okay.
I don't know exactly how to purposely disassemble some of the patterns, but what I know is that by controlling the acoustic mode, for example, instead of a standing wave, you apply a traveling wave so that you can generate acoustic streaming, or you call mixing. This mixing can help disassemble those particle aggregation. I hope that helps.
Yeah, so I was trying to get at, if you are making organoids, let's say with 4 different cell types, let's say for liver, you're putting hepatocyte, stellate, Kupffer cells, and maybe you think that, we don't want too many Kupffer cells. Maybe you can detach some and then bring more cells and attach those type of operation, I was thinking.
Right. Yeah, I think that's possible. You can control the cell concentration in the media, and by controlling the power, and also by controlling the frequency, we can also control the number of cells in each cluster. That's feasible, and the people have shown that.
I see. People also manipulate cells with DEP, but they also claim DEP may be a little bit dangerous to cells or impair cell viability. How about your method? Would that impair the cell viability?
Okay, yeah, that's a good question too. EP have requirement and on the median as well, so that's some limitations. For acoustic, it all depends on the power level. If the power is too high, then it will hit the cell and then kill the cell, of course, right? As I show here, I use different power level for different purpose. For a purpose where you don't want to hurt the cell, then you need to use medium low power. And we have shown that there's no side effect to the cell at all based on our so far, based on our observation and the study. The only drawback or the trade-off using low power is that it takes longer time. For example, in low power, it takes maybe 1 second or 2 seconds to assemble the cell. While in high power level, you only take half second or 0.1 second. But it doesn't matter, right? For assembly project, 1 second, 2 seconds, it doesn't matter. So I'm confident about the biocompatibility of the acoustic wave.
I see. Well, that's all the questions I have. Thank you for the great seminar. Appreciate your time, Professor Ding.
Thank you, Mehmet, and thank you all.
Have a nice day.
Thank you, you too.
Have a nice day, everyone.